So ordinary differential equations, that's and which class is this? This is our 8th class. So today is Wednesday, 28th. And tomorrow is a Thursday, but CUNY follows a Monday schedule. So lecture 9 is tomorrow. Same time, same place. And we're going to begin today to talk about chapter 5, which is linear second order ordinary differential equations. And the first section is just a general introduction, general theorems about homogeneous linear second order equations. And the second section is about the second order equations with constant coefficients. And when we finish section 5.2, I think we will have our first midterm exam, which will be tentatively on Wednesday, October 19th, in class. So the exam will be given on campus for everybody. So this is exactly 3 weeks away. So 3 weeks fair warning about first exam. Any questions about that?
Is there going to be a review sheet?
Yes, but the review sheet will basically be a list of problems that covers everything. So the homeworks are like a review sheet, but maybe longer than a normal review sheet. But I will put together a review sheet for the first exam. So, okay. So what is a homogeneous second order linear ordinary differential equation? So a second order ordinary differential equation means the unknown is a function of one variable, and the equation involves the first derivative and the second derivative of the function, but no higher derivative. And linear means it can be written in the following form. If your unknown function is y, the second derivative plus some function of x times y prime plus some function of x times y equals f of x. So this is a second order linear ordinary differential equation. And this equation is homogeneous as usual if the right-hand side is 0. So a homogeneous equation looks like y double prime plus p of x y prime plus q of x times y equals 0. And we're going to spend 2 weeks studying these homogeneous equations. Then we'll have the midterm, and then we'll look at non-inhomogeneous equations. So the basic theorem about such an equation says the following. And again, because the prerequisites for this class are rather simple, namely 3 semesters of calculus, we don't know enough, we don't have enough mathematical tools to prove the following theorem, but you have to know what it says, and implicitly or explicitly, we use it all the time. So in the counting system that's used in the text, this is theorem 5.1.1, chapter 5, section 1, in the first theorem in the section, and it says the following. Suppose we have functions p and q that are continuous on some open interval from a to b, that x naught be any point in this interval from a to b, and let k naught and k1 be any real numbers. So we have the following initial value problem. Find a function y that solves the differential equation y double prime plus p of x y prime plus q of x y equals 0. So this is a second order linear homogeneous differential equation, and it satisfies the initial conditions that the value of y at the point x naught is k naught, and the value of the derivative of y at x naught is equal to k1. So this is the initial value problem. And the theorem says that this problem always has a solution, and the solution is unique, has a unique solution y valid everywhere on the interval from a to b. So this is the fundamental theorem, that is, we use all the time. This tells us that every one of our problems has a solution. Having a solution is different from being able to find the solution, but every one of these problems has a solution. Now, there's one special case which follows immediately from this theorem. Suppose we had the initial value problem, y double prime plus p of x y prime plus q of x y equals 0, and the initial values are that y at x naught and y prime of x naught are both equal to 0, then the function y equals 0 for all x is a solution, because if you plug in y equals 0, you get 0 equals 0, and y prime at every point are 0. So this is in fact the unique solution, because there's this is a solution, and this is the only one. So this is sort of the trivial case, right? If you want to solve this equation when the function y, which is 0 at x naught and whose derivative is also 0 at x naught, y equals 0 is the only solution. So, okay. So let's look at some examples. So if any of you study physics, you'll know that these are fundamental equations in physics in many cases, many instances. So suppose we have this differential equation, y double prime minus y equals 0. So this is of the form, if you like, y double prime plus p of x y prime plus q of x y equals 0, where p of x is 0, because there's no y prime term there, and q of x is equal to minus 1, right? Either this be 0 and this be minus 1, this is the equation that you get. And these functions are continuous everywhere, from minus infinity to plus infinity. So for any initial values, x naught, k naught, and k1 in this notation, there will be a unique solution valid on the whole line from minus infinity to plus infinity. What are some examples of solutions of this equation? So again, this is the equation y double prime minus y equals 0. So one solution is y1 equal to e to the x. Because if y1 is e to the x, y1 prime is e to the x, y1 double prime is e to the x, and e to the x minus e to the x is 0. Another solution is y2 equals e to the minus x. If you differentiate this once, you get y2 prime is minus e to the minus x. If you differentiate this a second time, y2 double prime minus times minus is plus e to the minus x. And y2 double prime minus y2, again, is 0 because these are the same thing. So here we have two different solutions of this differential equation. Suppose I let C1 and C2 be arbitrary constants. And let y be equal to C1 times the function y1 plus C2 times the function y2. An expression like this is called a linear combination of y1 and y2. And I claim for every choice of constant C1 and C2, this is a solution. So let's just check. That's y. So y is equal to C1 e to the x plus C2 e to the minus x, right? Because y1 is the function e to the x and y2 is the function e to the minus x. So if I differentiate this, I get C1 e to the x minus C2 e to the minus x. If I differentiate a second time, I get y double prime is C1 e to the x. Again, minus times minus is plus C2 e to the minus x. So if I take y double prime minus y prime, that's C1 e to the x plus C2 e to the minus x minus y, not y prime, minus C1 e to the x plus C2 e to the minus x. These cancel and you get 0. So for every choice of constants, C1 and C2, this linear combination of e to the x and e to the minus x is a solution. Any questions about this? Any questions about the fact that each of these functions is a solution all by itself, and then every linear combination is? So suppose we actually have an initial value problem, IVP. Find a solution of this differential equation, y double prime minus y equals 0, that satisfies the initial conditions, y of 0 is 1, and y prime of 0 is 3. So this is, I'm letting x naught equal 0, k naught equal 1, k1 equal 3 in the notation of the theorem. So let's see if we can find some constant C1 and C2 such that y1 equals C1 e to the x plus C2 e to the minus x. Sorry, not y equals C1 e to the x plus C2 e to the minus x satisfies these conditions. Again, this is equal to y, and y prime is C1 e to the x minus C2 e to the minus x. So if I evaluate this at 0, y of 0 is C1 e to the 0 plus C2 e to the 0. E to the 0 is 1. This is C1 plus C2, and we want that to equal 1. And if I evaluate y prime at 0, that's C1 e to the 0 minus C2 e to the 0. That's C1 minus C2. And I want that to equal 3. So I will have a solution of the initial value problem if I can find constants C1 and C2 that satisfy these two linear equations. But this is just solving two linear equations and two unknowns. If I add them, I get 2C1 equals 4. So C1 equals 2. If C1 equals 2, C2 has to be equal to -1. Because 2 minus 1 is 1. And 2 minus minus 1 is 2 plus 1 is 3. So for this initial value problem, the solution is y equals C1, 2e to the x, plus C2, that's minus e to the minus x. So this is the solution of the initial value problem. This function solves the differential equation. When x equals 0, y is equal to 1. When x equals 0, y prime is equal to 3. Okay. Any questions about that? Okay, this is a very important differential equation, y double prime minus y equals 0. Another differential equation, second order linear homogeneous equation, which comes up often in many applications, certainly in physics, when you look at things that oscillate, a kind of wave motion. You have the equation y double prime plus some positive constant, I'll write it as omega squared, y equals 0. So let's take omega to be a positive number, right? So this is not 0. And omega squared is certainly positive. So I want to solve this differential equation. So again, this is of the form y double prime plus p of x y prime plus q of x y equals 0, where in this case, p of x is 0 and q of x is the constant omega squared. So for any initial conditions, this differential equation will have a unique solution from minus infinity to plus infinity, because these functions, p and q, they're certainly continuous from minus infinity to plus infinity. What is one solution of this equation? You could take y1 to be cosine omega x, right? Cosine, what's the first derivative? First derivative of the cosine is minus the sine, omega x. So by the chain rule, we get minus omega sine omega x. We differentiate a second time, the derivative of the sine is the cosine. When you differentiate sine omega x, you get omega cosine x. You get minus omega times another omega, makes this omega squared, cosine omega x. And y1 is cosine omega x. Y1 double prime is minus omega squared cosine omega x. So y1 double prime plus omega squared y1. Y1 double prime is minus omega squared cosine omega x plus omega squared times y1 cosine omega x minus omega squared plus omega squared gives us 0. So this is one solution of the differential equation. Another solution is y2 equals the sine of omega x. And we can check exactly the same way. Y2 prime is omega cosine omega x. Y2 double prime is minus omega times omega squared sine omega x. And if you multiply, if you take y2 double prime plus omega squared y2, again, you get 0. If I take y2 double prime plus omega squared y2, this is minus omega squared sine of omega x plus omega squared sine of omega x. Again, these cancel and I get 0. So y1 and y2, the cosine and the sine, are two solutions of this differential equation. And just as in the previous case, you can check for all scalars, all constants C1 and C2, the linear combination y equal C1y1 plus C2y2. That's C1 times the cosine of omega x plus C2 times the sine of omega x. No matter what number C1 and C2 we pick, this function will also solve the differential equation. Okay. Any questions about this so far? So suppose we have the initial value problem, y double prime plus omega squared y equals 0. Find a solution of this differential equation which satisfies the initial conditions that y of 0 is 1 and y prime of 0 is equal to 3. So here is my second order homogeneous linear differential equation. And here's an initial condition. We're specifying the values of y and y prime at 0. So we know that any choice of constants C1 and C2, for any choice of constants C1 and C2, this is a solution. So we can ask, can we find C1 and C2 such that the linear combination y satisfies these conditions? That is, y of 0 equals C1 cosine of omega times 0 plus C2 sine of omega times 0. Well, cosine of 0 is 1. This is just C1. Sine of 0 is 0. So y of 0 is just C1. Y prime of 0, if we differentiate this, we get minus omega C1 sine of omega times 0 plus omega times C2 cosine of omega times 0. So again, sine of 0 is 0, cosine of 0 is 1. This is equal to omega times C2. And we want y of 0 to be equal to 1, so C1 equals 1. And we want y prime of 0 equal to 3, so omega C2 equals 3, which means C2 is going to equal 3 over omega. So for the initial value problem, this differential equation with this initial condition, the unique solution is y of x equals C1, which is 1, times cosine omega x, plus 3 over omega sine of omega x. Any questions about this? All right. So I want to keep doing examples, and I'm picking examples from the book, which makes it easier to follow when you study at home. So let's look at a slightly more complicated problem. So in the text, this is example 5.1.3. And we have the differential equation x squared y double prime plus xy prime minus 4y equals 0. So this is not quite in the form that I described a linear second order equation. For us, the linear second order equation looks like y double prime plus p of x y prime plus q of x y, if it's homogeneous, equals 0. And the coefficient of y double prime is 1. Here, the coefficient of y double prime is x squared. But I can divide by x squared if x is different from 0. So for x different from 0, this equation would be the same as y double prime plus x over x squared y prime minus 4 over x squared y equals 0, where x over x prime is 1 over x, y double prime plus 1 over x y prime minus 4 over x squared y equals 0. And here, p of x is 1 over x, and q of x is minus 4 over x squared. So these functions are not continuous on the whole line. These functions are continuous on two different intervals. So we actually have two different problems. These are continuous on the interval from the open interval from 0 to infinity, and on the open interval from minus infinity to 0. These are open, so the endpoint 0 doesn't count. So this is 0. On this open interval, these two functions are continuous. And on this open interval, these two functions are continuous. So if we take any positive value for x naught and look at an initial value problem, this equation will have a unique solution from 0 to infinity. And if we take a number x naught that's negative, the different and some initial value problem will have a unique solution from minus infinity to infinity. What are two solutions of this differential equation? Well, one solution is if I take the function y1 equals x squared. If y1 equals x squared, y1 prime is 2x, and y1 double prime is 2. So if I plug that into this equation, what do I get? And I can plug it in. This is continuous everywhere. I can plug it into either one of these equations. If I plug it into the original equation, I get x squared times y double prime times 2 plus x times y prime, which is 2x, minus 4 times y1, which is x squared. So this is 2x squared plus 2x squared minus 4x squared. That equals 0. So this function solves the first equation. And if I put it into the second equation, we would also get a solution. We would get y double prime, that's 2, plus 1 over x squared times y prime, which is 2x, minus 4 over x squared times y double prime is 2 plus 1 over x, y prime, which is 2x, minus 4 over x squared times y, which is x squared. I get 2 plus 2 minus 4, which is again 0, which checks. So I could use either of these two equations to check the solution y1. But another solution is called y2 is 1 over x squared. If y2 is 1 over x squared, which is x to the minus 2, the derivative is minus 2x to the minus 3, or minus 2 over x cubed. And the second derivative is minus 2 times minus 3 is 6, x to the minus 4. which is 6 over x to the fourth. And again, if I plug this into either one of these equations, let's just plug it into the first, say x2y double prime plus xy prime minus 4y, that's x squared, y double prime is 6 over x to the fourth, plus x times y prime, which is minus 2 over x cubed, minus 4 over x squared times y2, which is 1 over x squared. So this is 6 over x squared minus 2 over x squared minus 4 times y prime minus 4 over x squared. 6 minus 2 minus 4 is 0. So this is also a solution of the differential equation. And this function is defined either from 0 to infinity or from minus infinity to 0, but not at 0. So suppose we have this differential equation and the following initial value problem. So this was my differential equation, x squared y double prime plus xy prime minus 4y equals 0. And I want y of 1 to be equal to 2 and y prime of 1 to be equal to 0. These are my initial conditions. So I know that x squared and 1 over x squared are solutions of this equation. So if I take any linear combination of them, this will also be a solution. And if y is c1x squared plus c2 1 over x squared, y prime is 2c1x. The derivative of x to the minus 2 is minus 2 x to the minus 3. So let's evaluate these at x equal 1. So y of 1 is c1 plus c2, and we want that to be equal to 2. And y prime of 1 is 2c1 minus 2c2 when x is equal to 1. And we want that to be equal to 0. If I divide this equation by 2, that's the same as c1 minus c2 equals 0. And my first equation was c1 plus c2 equals 2. If I add these equations, I get 2c1 equals 2, so c1 is 1. If c1 is 1, c2 has to be equal to 2. So my solution for this differential equation, satisfying this initial condition, it's y equals x squared plus 1 over x squared. That's the solution. When x is 1, y is 2. When x is 1, y prime is 0. That's the solution of the initial value problem. Any questions about this? This is very nice stuff. So I can write down as a theorem the fact that we've been using more generally. So chapter 5, section 1, the second theorem, so theorem 5.1.2, if y1 and y2 are solutions of the homogeneous second order linear ordinary differential equation, y double prime plus p of x, y prime plus q of x, y equals 0, then, see, on some interval from a to b, then for any constant c1 and c2, y equals c1 y1 plus c2 y2 is also a solution on the same interval from a to b for all constants c1 and c2. So if you have this homogeneous linear ordinary differential equation, if you take any solutions y1 and y2, every linear combination of them is a solution. And you can check this just by plugging into the equation and doing the arithmetic. And the important situation is when not only is every linear combination of y1 and y2 a solution, but every solution is a linear combination of y1 and y2. So we say that this pair of functions, y1, y2, is a fundamental solution of my differential equation, call it star, if every solution is of the form y equals c1 y1 plus c2 y2. So it's not true if you take any two solutions of a differential equation, they always form a fundamental pair of solutions. But if you have a pair of solutions with this extremely important property that every solution can be written as a linear combination of those two functions, y1 and y2, then we say this pair of functions is a fundamental solution or a fundamental set of solutions. Fundamental set of solutions of the differential equation. Now, here's our linear y double prime plus p of x y prime plus q of x y equals 0. This is our homogeneous linear second order equation. If y1 and y2 are solutions, and y2 is actually some constant times y1, then y1, y2 is generally not a fundamental solution, because every linear combination of y1 and y2 would really just be a multiple of y1. So this is sort of the bad situation. And we say that two functions, y1 and y2, are linearly independent. So if you happen to have taken linear algebra, you're familiar with this term, but we don't really need linear algebra. We say that two functions, y1 and y2, are linearly independent on the interval from a to b if y2 is not a scalar multiple, a constant multiple of y1. So for example, if you had y1 equal 3x to the fourth and y2 equals 5x to the fourth, then y2 is 5/3 times y1, because 5/3 y1, this is 5/3 times 3x to the fourth, that's 5x to the fourth. So here, y2 is a constant multiple of y1. So these two functions are not linearly independent. But for example, if I take y1 equal to e to the x and y2 equal e to the minus x, these are linearly independent. Because if y1 is some constant c times y2, that means that e to the x is some constant times e to the minus x. That means e to the 2x equals a constant for all x. And this is absurd, right? Because this exponential function is not a constant. So these two functions are linearly independent. And again, all the theorems I state are important, but the proofs are somewhat sophisticated, so we don't prove them, but you have to know what they say. So the third theorem in this section 5.1 says the following. Again, P and Q are continuous functions on the interval from A to B. The set y1, y2 of solutions, so these are two solutions of my homogeneous equation, y double prime plus p of x y prime plus q of x y equals 0. This set of solutions is fundamental if and only if these two functions y1 and y2 are linearly independent. So if you have a differential equation of this form, and you find two particular solutions, and you can show that neither of the solution is a constant multiple of the other, then that pair of solutions is fundamental. Every solution is a linear combination of them. So that's theorem 5.1.3, and you should think of that for a minute or two, because it's important. So let's think about this a little bit more, because it is very important. As always, we write our equation in the form y double prime plus p of x y prime plus q of x y equals 0. And p of x and q of x are continuous, as continuous functions, on some open interval from A to B. Suppose y1 and y2 is a fundamental set of solutions. So what does that mean? That means that for all points x naught between A and B, and constants, numbers k0 and k1, we can solve the equations. That means find C1 and C2 such that C1 y1 at x naught plus C2 y2 of x naught is equal to k naught, and C1 y1 prime at x naught plus C2 y2 prime at x naught equals k1. That is, we can find C1 and C2, so if we take y to be this linear combination C1 y1 plus C2 y2, this linear combination of y1 and y2 is a solution of the differential equation that satisfies these initial conditions. This is y of x naught is equal to k naught, y prime of x naught is equal to k1. Let's try and solve these equations. So this is, you can think of this as two linear equations and two unknowns, and the unknowns are the constants C1 and C2, the numbers C1 and C2. So for example, if I multiply the first equation by y2 prime and x naught, I get C1 y1 of x naught, y2 prime at x naught, plus C2 y2 of x naught, y2 prime of x naught equals k naught y2 prime of x naught. So I'm going to be eliminating C2. And I multiply the second equation by y2 of x naught. I get C1 y1 prime of x naught, y2 of x naught, plus C2 y2 of x naught, y2 prime of x naught equals k1 y2 of x naught. And these two expressions are the same. So if I subtract, I get C1 y1 of x naught, y2 prime of x naught minus y1 prime of x naught, y2 of x naught, this minus this minus this is 0, equals k naught y2 prime of x naught minus k1 y2 of x naught. Now, if this expression in the square brackets happens to be 0, the left-hand side is 0, and the only way I would be able to solve this equation is if the right-hand side was 0. If this is different from 0, I can solve for C1. If this is different from 0, C1 will be equal to k naught y2 prime at x naught minus k1 y2 of x naught divided by this expression in the brackets, y1 of x naught, y2 prime of x naught minus y2 of x naught y1 prime of x naught. Remember, let's just go back. Let me just review what I just did. So everything has a chance of making sense. Here, I start with my second order differential equation. It's linear and it's homogeneous. And I suppose y1 and y2 are a fundamental set of solutions. So what that means is if I take any x naught between a and b, and any constants k naught and k1, there's always some linear combination of y1 and y2, c1 y1 plus c2 y2, such that this function y satisfies the differential equation and the initial condition that y at x naught is k naught and y prime of x naught is k1. But y of x naught, that's just this evaluated at x naught, and y prime at x naught is this evaluated at x naught. I get these two equations, and that C1 and C2 satisfy. So I want to solve these equations for C1 and C2. So this is just high school algebra. If I eliminate C2, I get C1 is equal to this. If I cross multiply, I get this equation. The only way this equation is solvable for all possible choices of k naught and k1 is if this is non-zero. If I eliminate C1 and solve for C2, I would get C2 is equal to, I have the same denominator, y1 of x naught, y2 prime of x naught, minus y2 of x naught, y1 prime of x naught. And my numerator is y1 of x naught is k1 y1 of x naught minus k naught y1 prime of x naught. And again, this denominator has to be 0 for C2 to be defined for all possible choices of K1 and K2. So let me just keep this here in front of us. So we have y double prime plus p of x, y prime plus q of x, y equals 0. I want a solution where y of x naught equals k naught, y prime of x naught equals k1, and I want y to be some linear combination of these fundamental solutions, c1 y1 plus c2 y2. And there's a solution if this denominator is different from 0. So let me just recall 2-by-2 determinants. This is just an algebraic shorthand, if you like. If I have an array A, B, C, D, the determinant of A, B, C, D, so this really means determinant. It's just the cross multiply AD minus BC. So this is just, if you haven't seen it before, now you've seen it. That's all there is to it. This is just a definition of a 2-by-2 determinant. So, or if you like, it's just notation. If you have something of the form AD minus BC, I can write it like this. So my denominator for C1 and C2, they're the same. That denominator is y1 of x naught, y2 prime of x naught, minus y2 of x naught, y1 prime of x naught. So if I think of this as AD minus BC, this is like the determinant, where this is y1 of x naught, y2 of x naught, y1 prime of x naught, y2 prime of x naught. Right? That is, this determinant, AD minus BC, is exactly this. So this is the denominator in this expression. And we give this a name and a notation. We call this W at x naught. So W is a function of x. It's the determinant of y1, y2, y1 prime, y2 prime. And this function has a name. It's called the Ronskian of the functions y1 and y2. So the Ronskian of two functions is this 2 by 2 determinant. If we look at the numerators of C1 and C2, that also is a difference of products. Let me just write this down in determinant form. If I have K naught y2 prime at x naught minus K1 y2 at x naught, this is the determinant of K naught y2 prime of x naught, K1, oops, let me write it differently, it's the same thing, but K1 y2 of x naught. And the numerator for C2 is K1 y1 of x naught minus K naught y1 prime at x naught. I can also write that as a determinant. I'll put K naught K1 here, y1 of x naught, y1 prime of x naught. So in my solution of the differential equation, where I had to solve two equations in two unknowns, the unknowns were C1 and C2. In terms of determinants, C1 is K naught K1 y2 of x naught, y2 prime of x naught, that determinant over the Ronskian evaluated at x naught, and C2 is the determinant K naught K1 y1 and x naught, y1 prime of x naught prime over the Ronskian evaluated at x naught. And if you remember high school algebra, this is exactly Kramer's rule for solving two linear equations. All right, so this is perhaps a lot to chew over at one time. Let me just review what I said. So you have to know the notation for a 2 by 2 determinant. A, B, C, D, this is defined to be AD minus BC. That's the notation. So if you have functions that are differentiable, y1 and y2, from them we define the Ronskian W, which is y1, y2, y1 prime, y2 prime. So this is a function of x. This is y1, y2 prime minus y2, y1 prime. It's a function of x. And if we have the differential equation, y double prime plus p of x y prime plus q of x y equals 0, with the initial condition that y of x0 is k0, y of x1 is k1, and y1, y2 is a fundamental set of solutions, then the solution of the initial value problem is y is c1 y1 plus c2 y2, where c1 and c2 are given as fractions of determinants. The denominators are the Ronskians at x0. That better be different from 0. I'll come back to that in a moment. And the numerators are the determinants k0, k1, y2 of x0, y2 prime of x0, and k0, k1 in the second column, y1 of x0, y1 prime of x0. And the fourth theorem in this section, theorem 5.1.4, says if you look at this Ronskian, either w of x is different from 0 for all x in the interval from a to b, or w of x is identically 0 for all x in the interval from a to b. So if you have two solutions of a differential equation and you look at the Ronskian, either the Ronskian is identically 0 or it's never 0. So like, it's not a function like, for example, cosine x, which sometimes is 0 and sometimes is not. This Ronskian is either always 0 or never 0. And I think maybe I'll wait until tomorrow to prove this, but let's just look at an example, just to get a little bit more familiar with this. There also is an expression for the Ronskian as an integral. So this is a theorem or a formula due to a mathematician named Abel. So this is Abel's formula. You have y double prime plus p of x y prime plus q of x y equals 0, and y1 and y2 are a fundamental solution of the equation. Then the Ronskian, and you take x0 between a and b, the Ronskian is the value of the Ronskian at the point x0 times the integral, times e to minus the integral from x0 to x of p of t dt for all x between a and b. So in terms of the differential equation, this is a formula for the Ronskian. So let's try to calculate this for the three examples we looked at already. So the first example we looked at was the differential equation y double prime minus y equals 0. And we had two solutions, y1 equals e to the x, and y2 was e to the minus x. And this is a fundamental set of solutions. So what is the Ronskian in this case? So this is y1, y2, y1 prime, y2 prime. So y1 is e to the x and y2 is e to the minus x. Y1 prime is e to the x. Y2 prime is minus e to the minus x. If you calculate this determinant, you get e to the x times minus e to the minus x minus e to the minus x times e to the x. This is e to the x times e to the minus x is 1. This is minus 1 minus 1. This is minus 2. So this Ronskian is equal to minus 2 for all x. By the way, for this differential equation, p of x is 0. So the integral from x naught to x, p of t dt, you're just integrating 0, it's 0. So Abel's formula, w of x equals, and any value minus 2, w of x naught, e to the 0, which is minus 2. I mean, it's consistent. And then we look at the second example, y double prime plus omega squared y equals 0. We had two fundamental solutions, cosine omega x and sine omega x. What is the Ronskian? As a function of x, you take y1 and y2 and y1 prime, you differentiate this, you get minus omega sine omega x, differentiate this, you get omega cosine omega x, compute the determinant, you get omega cosine squared x minus times minus is plus, so plus omega sine squared x. That's omega times cosine squared x plus sine squared x. This is 1, this is omega. So again, this is constant. Okay, well, so we actually, we did a lot today because the subject of second order equations is much more complicated than the subject of first order equations. And we're developing here the general theory of homogeneous second order equations. And we'll continue that tomorrow. Next week we have class on Monday and we'll begin to look at the special case of second order linear homogeneous equations where the functions p of x and q of x are constants, as they are in these two examples. And we'll spend a lot of time working on that. Okay. Any questions about any of this? Anything that we've done for today? If not, then we will quit for the morning. That's it. Be well, everyone.
Have a good day, Professor.
Thank you. You too.